Hello everyone. The previous lecture I discussed the technique, the nuclear analytical technique based on neutrons, that is neutron activation analysis, and also discussed some of the applications of this technique in different areas. Today I will discuss another nuclear analytical technique called ion beam analysis technique. As the name suggests, in ion beam analysis technique, we use the charge particle beam, and the charge particle beam may have different types of reactions with the nuclei in the target, and depending upon the type of reactions that are happening, we have different nuclear analytical techniques. So by this schematic, I will first just introduce what are the techniques that I am going to discuss in this lecture. So when the low energy ion beam, it could be proton, alpha, or even heavier ions, they bombard the target, then there could be backscattering of the projectile. So the backscattering of the projectile is like Rutherford backscattering, and there is as we will discuss in more details, the specific relationship between the backscattered energy and the mass of the isotopes in the target material, and therefore we can identify the elements of the isotopes present in the target, and later on we can even find out their concentrations, depth of field. So this is a RBS, is the Rutherford backscattering spectrometry, is a very well-known ion beam analysis technique in material characterization. Now, second type of reaction can be that the projectile hits the nucleus and gives a recoil. That means the atoms, the target, are taken out of the target material. So they come out of the target material and they can be detected by suitable detector systems. So the recoils which are emitted in the forward angle, the forward recoils, are detected to tell about the constituent of the target. So this is called the elastic recoil detection analysis. It is purely elastic scattering between the target nuclei and the initial projectile beam. And this also can be used to characterize the different types of materials. There could be another type of, there could be nuclear reactions between the low energy ion beam and the nuclei in the target material. And these nuclear reactions can give rise to the gamma rays. So if you detect the gamma rays by from these nuclear reactions, then the analysis based on the nuclear reactions is called NRA, nuclear reaction analysis. And one of the variants of this is particle induced gamma emission, PG. Mostly protons or neutrons are used. So they are actually similar techniques, but the difference will become clear when we discuss each technique in the present lecture. So in nutshell, these are the four types of nuclear reactions or different interactions which we will be utilizing in the different nuclear analytical techniques: the RBS, the ERDA, the NRA, and PG. Also, you will see when the projectile beams interact with the target atoms, they can cause ionization in the atomic shells, like predominantly K shell ionization can take place, and this ionization of the K shell electrons will lead to emission of X-rays. So particle induced X-ray emission, though it involves the atomic orbitals, this also is considered to be an ion beam analysis technique, and mostly people use protons. So I will not discuss this particular. Basically, this gives you the composition of the material. Different elements will have characteristic X-rays, and those X-rays can be detected by a suitable detector, and the peak area of the X-ray peaks will tell you the concentration of the particular element in the target material. So you may have to have standards, and so it is similar to X-ray fluorescence, where you use X-rays to bombard the target material, and or even you can use gamma ray, or even you can use beta particles. So X-ray, the immediate X-rays are characteristic of the elements. So PIXI and HRF, these are other techniques which are used in routine compositional analysis of different types of material. While the ion beam analysis techniques like RBS, ERDA, NRA, and PG, they offer much more advantage over simple techniques like PIXI and XRF, and which will become clear. So this is not just routine analysis, but they involve the detailed analysis of the target material, the processes that one is studying, and so on. Okay, so let me first discuss the fundamentals of Rutherford backscattering spectrometry. As the name itself implies, it is based on the Rutherford scattering of the projectile by the nuclei present in the target material. And the two important principles behind this are, one is that when a projectile is being backscattered by the target nuclei, there is a precise relationship between the energy of the scattered particle, that is the projectile scattered, and the mass of the scattering atom. So basically it is an elastic scattering, and as we discussed in the lecture on nuclear reaction, in elastic scattering the kinetic energy is conserved, and you can calculate the energy of the backscattered ion exactly if you know the mass of the projectile target and the initial energy of the projectile, as well as the angle theta at which the scattering is going to take place. And so I have just given a schematic of this RBS. We have a projectile of mass m1, atomic number z1, and having energy E0, bombarding the target material, having, let us say, a particular nucleus it is interacting with mass and charge m2 and z2, and after the scattering, the projectile is coming out with energy E1. So theta equal to, let us say, 170 or 160, whatever it is. We will discuss y back angles very shortly. So you can, from the conservation of mass and energy and the conservation of linear momentum, set up the equation like we did it in that particular lectures to find out the mass of the target nucleus E3. If you recollect, we had solved that equation for energy E3 of M3, whereas here we will be determining the mass of M1 itself. You recall, M1 plus M2, M3 plus M4 for any nuclear reaction. But here it is elastic scattering, so it is M1 plus M2 only. This one we are trying, so it was the energy was E0, here energy is E1. And so this E1 is actually nothing but E3, you can say. And so you can solve this, that equation was solved, and the relationship between E3 and E1, or here E1 and E0, is given by this formula. Between it contains M1, M2, and theta. So this term can be clubbed as K. So the backscattered ion energy is K into E0. And the K is called a kinematic factor. It depends simply upon the masses and angles of the projectile target nuclei. So this tells you, so this is for the particular value of M2, there is a particular value of K. So that way you can find out what is the mass of the nucleus which was backscattering the projectile. The second relationship between the probability of scattering of the projectile and the Z of the target. And the cross section is given here. Probability means essentially the cross section. So the differential cross section d sigma by d omega per unit solid angle is given by Z1 Z2 E square upon 4E, where E is the projectile energy cosec 4 theta by 2. So you can see here, higher the Z of the target nuclei, higher is the cross section. So this will be made more clear that for higher Z nuclei, the sensitivity is higher. Cross sections are higher, meaning there will be more events. So you can then, from the determination of the number of particles that are scattered, or from the counts in the spectrum of the scattered particle, we can find out the concentration of the target nuclei. So the measurement of the energy of the backscattered particle gives you the mass number M2 in the target. You identify. So, and from the mass number, you can of course identify the elements. And from the number of scattered particle, so number of scattered particle, what do you know? Scattered particle, it will be Nt sigma I, and then you can say, so this sigma will be d sigma by d omega. So this is the number of particles into t time, and so this tells you the concentration of that particular target. Now let us ask the question, why back angles? And in fact, the RBS is done with the low energy ions. Energy of the projectile is low because we do not want to introduce any nuclear reaction. So it is simply Coulomb scattering. So you need to be below the Coulomb barrier. So there are no complications because of the nuclear reaction with the target. So it's a pure Coulombic scattering. So that energy of the projectile will be kept quite low. Not only that, the cross sections for this Rutherford backscattering are, if you see here, cross section for the scattering is 1 upon E square. So lower the energy, higher is the cross section for RBS, and therefore we go for low energy ion beams. So two aspects. Why the low energy ions? Because the cross section is inversely proportional to E square. So that is E0. So lower the energy of the projectile, higher the sensitivity for the RBS, and for sensitivity for detection of the concentration of the elements. So typically, people use 2 MeV alpha particle beams, so you will be below the Coulomb barrier for most of the target nuclei. In addition to this, there should not be any nuclear reaction, but that will complicate. It will unnecessarily introduce some radioactivity in the sample, and so it may become difficult to handle. So this is the reason for low energy. Second is that mass. Why back angles? So back angle is the difference in the particle energy, that E1 backscattered from different masses in the target nuclei, is maximum at most backward angles. So if you see here, if you put theta, so essentially you can say dm2 by d theta, the change in the mass with the angle. If you do an exercise, and you will find the differences between different masses. Suppose you have got cobalt, iron, nickel, different elements, so their masses are also different. They will add their energy, the energy of different masses will be widely spaced at most backward angle. dE1 by d theta will be maximum at theta equal to 180. But you cannot put theta at 180 degrees because that is the beam path. So you keep slightly away from 180, maybe 170, 160 or so. So that is the reason for back angle. So you want to resolve, for example, here, what I have shown here, M2, different M2s in the spectrum. So the charged particle, the projectile spectrum, if you record in the back angle, then you will see here, this is low mass, higher mass, higher mass. So this gap between these different masses will be maximum at most backward angle. So you can say the mass resolution is at most backward. Otherwise, at forward angle, they will all merge together. The gap will reduce. So you cannot resolve they may start overlapping. Secondly, as I mentioned, the cross section are proportional to Z square. D sigma by d omega proportional to Z square of the target elements, and so higher the atomic number of the nucleus that we are going to investigate, higher the sensitivity. because more events you will get. You can see here, this is the lower jet, medium, higher jet, and still higher jet. So higher the jet, higher the counts you will get. So they are more sensitive. And because of this reason, the RBS is ideal for detecting the high jet impurity in a low jet matrix. So mostly the applications of RBS involve determination of high jet impurities in a low jet matrix. Suppose you have got a plastic that you want to determine some impurities, metallic impurities, or iodine, bromine. Excellent technique for that kind of job. So there will be several applications. So that is one, determination of depth profiling of high jet impurities in a low jet matrix. Because of this, higher Z being more sensitive, and they appear at high energy, so you can distinguish them from the low jet matrix. And second is the depth profile. You can do depth profiling by RBS technique, because the backscattered ion energy will be different depending upon the depth from which the scattering is taken. I will elaborate this more using this cartoon. So you have a projectile of energy E0 bombarding the target, and I have shown a thick target. So there will be backscattering at every depth of the target. So from the surface backscattered projectile energy will be K into E0. K is the kinematic factor. So the energy is well known. For the particular M2, you can find out what is the energy, because K you can calculate exact. K depends upon M1, M2, theta. Now, as the projectile is traveling in the target material, it is losing energy, and every depth it will get backscattered. So let us say at a particular depth, we say this particular depth energy lost is delta E1. So the energy at this depth will become E0 minus delta E1. So a M2 at this depth will see a projectile coming at E0 minus delta 1 and backscattered from that side. So you are putting a detector here, D. So the backscattered energy at that point will be K into the kinematic factor into E0 minus delta E1. And again, the backscattered ion will lose energy delta E2, so minus delta. You can exactly calculate what will be the energy of the backscattered ion if it is backscattered from a particular depth in the target material, because the kinematics are very well known. The energy loss is very well known in a target material. You can find out, because the stopping powers are known, and you can find out the depth. So that is what is the, suppose you know the d by dx, you can find out the depth at which the backscattering took place. And so by recording the spectra of the backscattered particles, projectile particles, you can do depth profiling, and then you can also get the depth resolution. So impurity concentrations and at what depth they are, you can see. So depth resolution in RBS, delta X depends upon detector resolution, FWHM of the peak upon stopping power, d by dx. So you can determine the resolution of detector from the normal spectra, and then you can find out the stopping powers are known, you can find out the depth resolution. So I'll just give you some of the examples of RBS. So you can have RBS a thin target and thick target. So thin target means the projectile is passing through the target, it is not stopped by the target. So you can see here, I have shown here some of the RBS spectra using a 4 MeV proton beam at the, from a, we have an accelerator called folded tandem ion accelerator. And so these are the metal files of holmium, thulium, and thorium, and their thicknesses are in microns. So when the particle is going, so basically the objective was to see if there is a oxidation of this pyrophoric metal ions on the surface. If there is oxidation, there will be surface oxygen on the, so when the beam is hitting the surface, and so both front and back will backscatter. So oxygen at the front, this is the front, this is back. High energy is from the front and low energy is from the back, and this is the metal file. So that you can find out the thickness of the file, because you know the d by dx and you know the energy of the alpha or the projectile. And similarly, so for thorium, you can find out the oxygen concentration and the depth of the thickness of the foil. So this is the typical experiment with thin foils. If you have a thick target, the thick target means the projectile will stop in the somewhere in the middle, somewhere in the target, and so the high Z impurities will appear at a much higher energy than there will be a big hump because of the bulk material. So this is a RBS spectrum of gallium oxide deposited on a thick silicon foil. So on the surface, suppose you have got silicon foil and you have the gallium oxide on the surface and you see the backscattering. So the gallium peak will come at much higher energy, but the oxygen of gallium will be at much lower energy because the kinematics are dependent upon M2. And silicon will be somewhere here, and since silicon is very thick, the silicon will not appear as a peak, but it will appear as a thick edge type thing. So this is all due to silicon. So this is due to the thickness of this. Since it is very infinitely long, larger compared to the projectile range, you will see a hump. So thick targets will show a hump. And this is a very interesting experiment of multi-layers. There were several layers deposited of gadolinium oxide and silica layers, or each layer being of nanometers thick, and that could be seen in the RBS spectrum. But of course, if you want to have high resolution, then you require heavier projectiles like fluorine-19, because you require to have a more mass resolution. If you want to have higher mass resolution or higher resolution, you require to have heavier ions because the stopping powers are higher. So some of the applications of RBS in, like, this is a polymer inclusion membrane. These membranes are used for separation of metal ions like cesium and silver from the aqueous solution. So the constituents are cellulose triacetate, nitrophenyl octyl ether. This is the bulk material, this is a plasticizer, and this is the carrier molecule which will take the cesium, diamonyl naphthalene sulfonic acid. And this polymer inclusion are like polymer membranes, and you can take up cesium. So you want to know whether the cesium is distributed uniformly or in the sample or not, only on the surface. So that was the experiment. You can see depth of file of cesium in polymer inclusion membrane was studied by 5 MeV proton beam with a current of 3 to 5 nanoamperes. And now, since proton has got very low stopping power, depth resolution is only 1 micron, but then the thickness of these foils are up to 100 microns. So 1 micron is quite good. And this is the AFM of the polymer inclusion membrane. And you can see here carbon, oxygen, sulfur. So these are flat. That means the thickness, that means the polymer is uniformly distributed. And even the RBS spectrum of cesium shows that cesium is uniformly distributed in the entire membrane. So up to 100 micron, entire thickness of the membrane, the metal ion is distributed. So the idea was to see whether this carrier molecule, sulfur bearing molecule, is distributed uniformly in the membrane. Similarly, another experiment was Rutherford backscattering spectrometry of cesium diffusion in borosilicate glass. These borosilicate glasses are used for immobilization of the high level waste at our department. And so you want to have higher resolution. So we used fluorine-19 beam, 6 PNA. That resolution was 25 nanometer. So this is the typical experiment. The beam comes from here, hit the target, and then backscatter fluorine beams are measured by 2 detectors. This is so you have a glass sample, and on the surface we have cesium chloride evaporated. Then after the evaporation, you anneal this sample at different temperatures. So different temperatures, the cesium will go in the depth, and you are studying to what depth it has got diffused. So this depth profiling of cesium can be done using RBS, and then you analyze to go. So this is the RBS spectrum, and this gives the penetration depth versus cesium concentration, and the analysis of this gives you the diffusion coefficient of cesium in the glass pieces. These data are useful in subsequent analysis. Okay, another technique is elastic recoil detection analysis. We have not worked on this, but it is also an important technique. And it is in fact it's complementary to Rutherford backscattering spectrometry, because this technique is used for analysis of light elements in a heavier matrix. RBS we use heavier elements in lighter matrix, this ERDA lighter elements in heavier matrix. And why it is so? If you recollect the kinematic equation for elastic scattering, the energy of recoil, we can say E2, is related to energy, projectile energy into m1 m2 upon m2 square cos theta. And so the projectile mass, if projectile, you need to have, you are detecting the requires the forward direction. So if you have a heavier projectile mass, all the recoils will come in the forward direction. It will give you a bigger kick. The energy of the center of mass will be more, and so all the recoils come in the forward kick. So you put the detector in the forward angle and detect their spectrum by delta EE telescope. So you use delta EE telescope, thin delta E silicon detector and thick silicon, or you can use a delta E based on gas. And the stopping power is given by mz square by E into the electron density of the medium. Since you are putting the sample detector in the forward angle, let us say 15, 20 degree or 30 degree, if you have to, so the target may be thick because the heavy ion beam will not travel much. So what you want to do, you put the target in a glancing position. So small angle, maybe 15 degree or so. And so this is called a glancing position. At forward angle, you measure the, so the heavy ion beam is not passing through the target, but it may be appearing from, the recoils coming from different depths in the sample. So why heavy ions? Because we want the higher recoil energies and which will appear at the forward angles. And why low angles? Because with heavy ions as projectiles, recoils will appear at the forward angles only. The recoils will come in the forward angle only if you have a heavier mass. So ERDA essentially is used to detect low jet impurities in a high jet matrix. Typically, like you have 1 MeV per nucleon chlorine, so 35 MeV chlorine beam, and you have a thick detector and thin detector, and keep the angle at 15 degree or so. So I'll just quickly give you two applications of elastic recoil detection analysis. One of them is, so ERDA is essentially used for low jet impurity detection, hydrogen, helium, lithium, carbon, oxygen in a high jet matrix. And this, most of the time, these high jet matrices are high technology materials like porous silicon, diamond-like carbon films, silicon nitride, etc. And if you have a very thin target, like micron thick or even less, then you can use it in the transmission mode. It means this geometry, you don't need to put in the glancing angle. Beam can pass through this. So you have an iodine 127 beam of 140 MeV. You are determining the impurities in the molybdenum foil of 100 microgram per centimeter square thickness. So you can put detector at forward angle. And now you will get the spectra due to different impurities like carbon, oxygen in form of narrow peaks. And this is the iodine elastically scattered from molybdenum. So this is not of interest. And we have the molybdenum peak, the molybdenum recoils you will get. And so they were essentially wanted to see what is the carbon, the impurity. So it was basically carbon impurity, and the carbon content was found to be 75% of the molybdenum. So they are used in like nuclear physics experiment. We have a metal file and you want to know what is the impurity in the target. Normally the ERDA is studied in reflection mode because you will have thick target and you will be like micron thick sir. So you would like to know what are the elements present as a function of depth. So one of the examples I am giving you, the silicon nitride. It is a very, very technologically important material because of high hardness, good creep resistance, high wear resistance. It's a hard material, low coefficient of thermal expansion, chemically resistant, and increased mechanical strength, and finds applications in automotive industry, bearing, cutting tools, etc. So one of the studies was that glancing angle, they studied the recoils from the target. What is the target? The silicon and silicon nitride on a silicon substrate, you have thick silicon, and on which you sputter or evaporate, and you make a layer of silicon nitride. You can do even ion sputtering. And so under this position, so glancing angle and at forward angle, you see the spectrum. So the thickness of this silicon nitride was actually very thin. It was about 12 nanometers, 12 nanometer thick silicon nitride, and the composition is not known because you may be depositing by ion sputtering. But you can see here, you can get a flat concentration of nitrogen and silicon here, that is the bulk silicon, and you will see some impurities. These impurities are seen here, low Z impurities. And from the ratio of the nitrogen and silicon counts, this is silicon, they could find out that it is a Si3N4 silicon nitride, Si3N4, with a depth resolution of 2 nanometers. So, as I was mentioning, this ERDA is basically used in specific cases where you are looking for a particular information. It is not just routine analytical technique, but it is used in whenever you want a specific information about the material that you have developed. So that's all I have to say. In the next lecture, I will take the other two techniques, nuclear reaction analysis and particle induced gamma emission. Thank you very much.